requirements for this and how the methods that can be employed to assess and rank areas based on the sensitivity. In addition, an example of how one can assess environmental sensitivity will be provided. Today's presenter is Rich Belauskas. He is a marine biologist here at RPS-ASA, and he is focused on evaluating impacts to marine organisms. But before we begin, I would like to thank Peace for facilitating this webinar. Peace is part of the RPS training group, and they provide practical professional career training for the oil and gas industry. Their training is for upstream, midstream, and downstream, ranging from technical engineering and science to the management and from basic to skilled applications. To give a little background for those that may not be familiar with RPS-ASA, we were formerly known as Applied Science Associates, and we're now part of the RPS group. We have been conducting modeling in the marine environment since 1979 and doing it in over 100 countries. We've been providing services and custom solutions to sectors including the energy, environment, construction, defense, security, emergency management, transportation, and shipping. We've been providing environmental sensitivity analyses for government agencies for over 25 years. I'm going to hand the microphone over to Rich, and he's going to go through what he'll be talking about today, and I hope everyone enjoys today's webinar.
Thank you, Nicole. In today's presentation, we will cover the concepts of environmental sensitivity, specifically how it relates to marine environments and risk assessment. We will then discuss a scoping level, regionally based environmental sensitivity analysis for an oil spill, and we will finally take a quick look at a site-specific sensitivity analysis, examining a specific oil spill scenario. So why are we interested in this concept of environmental sensitivity? Well, for starters, it is an extremely interesting and to a degree enigmatic concept. It is an idea we want to wrap our heads around, but also a concept we know has no correct or true answer. From a more directed point of view, environmental sensitivity exists in some government regulations. For instance, the BOEM 5-year lease program requires the assessment of relative environmental sensitivity for each leasing area. Additionally, environmental sensitivity analyses may be a requirement for some NEPA documentation. Sensitivity analyses may also be useful in helping to improve planning and guidance for response to various impacts, and may provide rationales for compensation after the occurrence of a given impact, such as an oil spill. There exists no accepted definition for the concept of quote-unquote environmental sensitivity. In fact, while the Outer Continental Shelf Lands Act of 1953 states that decisions regarding exploration and development of oil leases will be based, in part, on the relative environmental sensitivity of different areas, this law does not define environmental sensitivity, and it provides no method to measure it. Indeed, environmental sensitivity is not a commonly applied concept in ecology as a whole. That said, there have been a wide variety of international efforts to develop methodologies that assess this concept, each for its own specific interest group. These methodologies share many similar concepts, but also diverge in assessment methods in other places. On the slide, you can see numerous example studies. So while there is no singular accepted definition for environmental sensitivity, there are many available in both government documentation and peer-reviewed journals. We will take a quick look now through a few examples. A comprehensive set of definitions is available online based on work funded through BOEM, which resulted in a report titled A Method for the Evaluation of Relative Environmental Sensitivity and Marine Productivity of the Outer Continental Shelf. BOEM defines environmental sensitivity as the vulnerability of an outer continental shelf planning area's ecological components to the potential impacts of outer continental shelf oil and gas activities in comparison to the same ecological components in other outer continental shelf planning areas. This definition has been subsequently modified to suggest that relative environmental sensitivity incorporates both the vulnerability and resilience of an outer continental shelf region's ecological components to the potential impacts of outer continental shelf oil and gas and offshore renewable energy activities in the context of existing conditions. From Laffoley et al., we find a sensitive habitat or species is one that is easily affected by human activity and is expected to only recover over a long period. Here we have an example that is pieced together from various other sensitivity studies to produce a definition that these authors prefer to any of the single contributing definitions. The degree to which a component responds to a pressure. Sensitivity is itself a function of the component's resistance to a pressure and its inherent resilience. A component is deemed to be highly sensitive when it has both low resistance and low resilience. From a paper published in Aquatic Conservation, we find that environmental sensitivity is the intrinsic intolerance of a habitat, community, or individual of a species to physical damage or removal from an area due to an external factor beyond the range of environmental conditions normally experienced. And here we have one I particularly like from Lieberknecht and Vincent, which has also been adopted by several other researchers. Sensitivity accounts for both the ease of damage to the feature by the activity and its ability to recover from that damage. Sensitivity is therefore assessed against particular activities rather than applied once to a feature. Looking through these definitions, we begin to see some major connecting points. Clearly, most definitions address the major components of the environment, species and habitats. These are the two simplest units with which we may consider the characteristics of a given environment. The next unifying concept is that of an external factor or stressor. This is the impact to which the environment is sensitive. In that last definition I presented from Lieberknecht, they effectively note that environments do not have inherent levels of sensitivity, but rather the concept of sensitivity can only be assessed against a specific impact type. Only then the sensitivity of the habitats and species of an area may be assessed when considering their resilience to a stressor, their potential impact from the stressor, and their speed of recovery once that stressor is removed. Therefore, in risk assessment, we need to address a specific stressor type in order to develop a sensible and objective result regarding environmental sensitivity. As we know, marine environments will have unique levels of sensitivity to different impacts such as dredging, offshore wind development, and oil spills. For the purpose of this talk, we are going to look at environmental sensitivity as it relates to oil spills. In fact, the model being presented today is specifically designed to only assess environmental sensitivity to oil spills. However, as you will see, the general framework of this model may be modified to assess environmental sensitivity to a variety of potential impacts. So as I mentioned, the specific project and framework I will be discussing today involves an environmental sensitivity analysis of the marine waters of Alaska. This work was funded and directed by NOAA, including the Habitat Restoration Center in Seattle and the Alaska Regional Office. The goal of this project was to develop an environmental sensitivity analysis methodology and incorporate it into a risk assessment framework in order to conduct a screening level analysis of the relative risk of oil spills to the marine waters of Alaska as a regional comparison. The results from this analysis are intended to provide NOAA, NERDA practitioners, and oil spill response restoration planners with an assessment of regions having high environmental sensitivity and high oil spill probability. Subsequently, this information can be used to help guide strategic planning and prioritize future research activities. As I showed in an earlier slide, there have been a wide variety of methodologies developed to assess environmental sensitivity. We began building our risk model loosely built after the Washington Oil Spill Compensation Schedule. This model part of Washington state law, provides a per gallon relative impact score for oil spills, considering the sensitivity of the locations oiled, relative density, and seasonal distribution of sensitive resources, and factors related to oil type. However, the Washington Compensation Schedule is specific in scope, particularly to the resources found in that state, and it required significant updating and expanding to be applied elsewhere. The Alaska risk model I'll be presenting today consists of three main elements, primarily composed of the sensitivity of the environment to oil spill impact. The model also includes probability of a spill based on past and projected incident rates, as well as maximum most probable discharge and worst case discharge volumes that could result from a future incident. However, today we will just be discussing the environmental sensitivity portion of this model, but from a risk assessment standpoint, it is important to consider the likelihood and potential magnitude of the impact or stressor being considered in the study. I'll also note that the sensitivity of socioeconomic resources is not included. This is directly an environmental model being presented. The sensitivity model is designed to compare sensitivity among different regions, so in that respect it is both spatially explicit but not entirely just a mapping exercise. Alaska was divided into 14 broad regions for analysis. These zones are based on the Marine Alaska Department of Environmental Conservation and Alaska Regional Response Team Contingency Planning regions. When developing your regions for analysis, you must be cognizant of what the final goal of your analysis is. Will the regions you are using or have created allow you to answer those questions? In this case, the regions were a priori decided due to existing regulations, but it will not always be so straightforward. And please keep in mind, this is just one example. This method and framework can be done for any area and any region of the world. Other considerations to include when assessing environmental sensitivity include the temporal scale at which the assessment occurs, and also the scale at which you want to consider the stressors. In this example, there is clearly an extremely wide range of potential stressors when considering an oil spill. There are potential orders of magnitude differences in impacts when considering different spill volumes, different spill probabilities, and different oil attributes, as environmental sensitivity may differ based on oil characteristics such as viscosity and aromatic content. Determining the appropriate level of specificity regarding the temporal scale of analysis, as well as the level of detail considered in the assessed stressor, is important to garner truly helpful results from your study. Here we have a flowchart of the overall environmental sensitivity methodology. This screening modeling methodology can be used anywhere in the world. Then results may be applied with different subsequent types of models, such as Lagrangian particle tracking models or cumulative use assessments. The following slides go through each element in more detail, but basically the model works to combine species and habitat information to calculate environmental sensitivity by region. There are many equations behind this model, which we will not be discussing today, but in general, marine habitat sensitivity is comprised of bottom type, submerged aquatic vegetation, and ice. Individual species scores are based on abundance, impact, and recovery, and then these each are summed to get sensitivity scores for each species group. That then produces environmental sensitivity for each region and season. This sensitivity metric may then be further modified to consider specific oil spill situations, such as different volumes and oil types. Though this model uses quantitative data where possible, it is also heavily reliant on categorical classifications of species. The hope is that these categorical inputs are designed to be completed objectively, allowing for a repeatable assessment of sensitivity. The environmental sensitivity model essentially operates by assigning sensitivity levels to specific species and habitats through various scoring mechanisms. We'll be discussing these scoring methods shortly. In overview, the purpose of this model is to reflect the relative sensitivity of the environment to oil spill impacts. Sensitivity, again, is based on habitats and species present in each region and season, and sensitivity scoring assumes that a spill would oil each habitat type and each species within a region. when in reality, of course, not all species and habitats would be oiled in a specific situation. Concentrating now on the habitat sensitivity pathway. The habitat portion of the environmental sensitivity model accounts for the sensitivity of the physical habitat itself, as well as for species occupying that habitat. The three main habitat categories considered include bottom habitat and SAV, shoreline habitat, and sea ice habitat. This model also includes consideration of protected areas and essential fish habitat, which are used to give additional weight to regions that have a high proportion of these special areas. While this does bring some aspects of social science into the model, we feel as though these specific protected areas do in fact represent areas that are more sensitive to oil spills. Each individual habitat type will interact uniquely with an impact or stressor, in this case oil. Some habitats retain oil for shorter time periods due to their physical characteristics. Likewise, some habitats and their biotic components are more prone to oiling than are others. This is accounted for in this oiling effect scoring. These quote-unquote scores are based off of the Washington Compensation Schedule and have been developed and vetted by experts in the oil spill field. Each habitat type sensitivity gets multiplied by oil effect scoring for acute toxicity, mechanical injury, and persistence of oil by shoreline type. Moving on to the species sensitivity pathway, we see that species sensitivity is comprised of three major parameters: relative abundance, a measure of population size within a region and season; impact, in the event of a spill, how severely would the species be affected; and recovery, in the event of a spill, how quickly would the species population be able to recover from the impact. We develop scoring criteria for each parameter and species group, including marine mammals, fish and invertebrates, and birds. Because these species groups interact in such unique ways with the marine environment, and as a result different stressors, in order to properly assess them, they must be considered their own respective groupings. Historically, the assessment of marine environmental sensitivity for species has focused on these three concepts: abundance, impact, and recovery. By working through as many existing environmental sensitivity assessment projects as possible, we developed this model species assessment in a comprehensive manner, pulling the most important pieces from each and coming up with a consensus of what concepts must be included. Relative abundance is assigned for each species, region, and time period combination. Abundance is consistently a point of contention in environmental sensitivity analysis. Are species that are rare within a region more sensitive because they represent such a small population and likely will have reduced recovery characteristics? Or rather, should abundant and representative species be considered more sensitive because they make up the majority of the community and any impacts will affect them the most? We have addressed this issue by making all species relative only to themselves, allowing for each to have potential equal value in the model. In this case, an endangered species endemic to a region of Alaska is just as important as, say, widespread forage fish. Additionally, because effort required to determine exact population levels for even well-studied species is extremely time-consuming, a relative abundance metric is utilized. Moving on to how impact scoring, which addresses the concept of when a spill occurs, how adversely will the species be impacted. Scoring is different for each species group, but covers the same themes of encounter potential, physiology, concentration, and indirect trophic effects. And note, impact scoring is specifically set for an oil spill. If you were assessing, say, the sensitivity of a region to being open to bottom trawling, the habitat use metric, including the one we see here in the top left, would be set up very differently, with species using demersal and benthic habitats being the most sensitive, as opposed to here, where surface and water column oiling is most detrimental to species. That said, the same themes of encounter, physiology, concentration, and indirect trophic effects should be considered regardless of the impact type being considered in your sensitivity analysis. I would like to reiterate that while we have come up with these scoring methods, they are influenced by many excellent earlier studies. And recovery scoring, addressing that when a spill occurs, how capable is the species of recovery from the negative impact? The same recovery scoring scheme is applied to all species and is used as a modifier to apply additional sensitivity to species that have low population levels, low reproductive capabilities, and/or small geographic ranges. A final key consideration in setting up an environmental sensitivity model is choosing which species are assessed within the model. The species selection process is very challenging, as it is obviously impossible to assess all the species which inhabit a particular region. Developing an objective methodology that accounts for various niches and behavior groups is critical to the model's success. Listed here are behavior groups that were represented within this model. It is important to also consider including both rare and abundant species, as well as both wide-ranging and endemic species. Now that you've seen the overall structure of the model, here's a quick refresher of the geographic regions assessed in the model. Here we have a poll in which I'd like you to vote on which region of Alaska you think has the greatest sensitivity to oil spills based on the species and habitats present within that region. It's just a guess. Feel free to guess on whatever region you suspect. Cook Inlet looks like the preferred region, and a very good guess. So here we have the results of the final environmental sensitivity scores for each region and time period, sorted by the yearly mean score. The highest sensitivity score we find is for the Aleutian regions, which did receive a few votes in the summer months. The Aleutians region also had the highest yearly mean sensitivity, followed by Norton Sound and the Kodiak region. The Bristol Bay and South Central Alaska regions have the lowest mean sensitivity. Overall, the greatest sensitivity occurred in late spring and early summer, while the lowest scores occurred in late fall. This result is driven mainly by the migration of species that spend the summer in Alaska. And here we have a breakdown of the different sensitivity components which contribute to the overall regional sensitivity. By examining these inputs, the main drivers of the environmental sensitivity for each region become apparent. For example, the high mean environmental sensitivity score for the Aleutians region is driven by high species sensitivity scores, particularly for marine mammals and fish and invertebrates. Conversely, the high mean environmental sensitivity for the Norton Sound region is driven by high mean habitat scores, which you see in the first column of HVS there, due to sensitive shoreline, bottom habitats, and high seasonal ice coverage. Some general conclusions from this scoping level sensitivities for Alaska include that environmental sensitivity is typically higher, as I mentioned, in the summer months than during winter, primarily due to that presence of migratory species during warmer months. In different regions, different environmental components, such as birds or shoreline habitat, contribute more significantly to overall regional sensitivity than do other environmental components. So this model has worked to identify sensitive regions which may now be further assessed. Let's build on this and quickly look at the Beaufort Sea region in a bit more detail to find out how we can expand upon this scoping level exercise in an environmental sensitivity analysis. So the environmental sensitivity model has identified the Beaufort Sea as having moderate to high environmental sensitivity, based primarily on having very sensitive habitats. Additionally, during summer months, there is high sensitivity to migratory bird populations. As such, we may want to explore a specific spill in more detail within this region. Here we have a completely theoretical spill location to the northwest of the Colville River Delta. And here we have an image of maximum floating oil concentrations for a theoretical 10-day subsurface release of 300,000 barrels of Alaskan North Slope crude in July that we've tracked for 50 days. So now we have moved past a scoping level analysis and can incorporate a more site-specific study into the impacts from a potential spill, including specific shoreline types and species specifically impacted. This, in fact, becomes a much more detailed and potentially time-consuming and costly endeavor, but because we have used our scoping level environmental sensitivity analysis to prioritize where effort should be allocated, there has been an effective use of resources. And we can analyze species-specific interactions with a spill scenario to determine areas that may be particularly sensitive based on habitats, breeding grounds, nesting areas, etc. So in conclusion, the benefits of the environmental sensitivity approach included that the various inputs, assessment criteria, and assumptions are all explicitly stated and analyzed in a quantitative manner when possible. The model is transparent and produces objective, repeatable results. Without such transparent, repeatable approach, it would be difficult to combine the many data sets that contribute to this model in any meaningful way. And though this model is designed to assess sensitivity to oil spills, other impacts may be assessed within this framework with minimal changes to the environmental sensitivity portion of the model. Despite the inherent limitations of such broad-scale assessment effort, regionally based environmental sensitivity analyses can provide valuable information to guide the prioritization of risk planning and further study. Again, I would like to thank the various funding sources that made this research and model development possible, including BOEM and NOAA. And we have a few upcoming webinars that you'll find here on the screen. And you can now I can now open up questions in chat if anyone has any specific questions they'd like to ask. So Nicole is wondering if a similar analysis or the same could be performed in other parts of the world. As I mentioned, though this study was completed in Alaska and the region set up there, this same methodology can be applied to any regional breakdown of any area in the world. You may have noticed that there were some specific concepts in this model that included surface ice and sea ice, which are, of course, specific to areas in the Arctic and Antarctic regions. So the model would need to be slightly modified to incorporate those concepts. But in general, the framework is possible to be used anywhere in the world. If we have any other questions, I'd be happy to answer them, or my contact information is on the screen, and I'd be very happy to include any other information you're interested in. Feel free to contact me. If there are no other questions, this will conclude our webinar today, and I appreciate you all joining this webinar.